So this is our second panel that we've got, showcasing some of the things we're doing at University of Exeter and around. We've got panelists Paul Halloran, Dan Bloomfield, Torsa Sengupta, Beccy Mitchell, and Iain Hartley. So if you can all come up one by one. Paul Halloran is at University of Exeter, an expert in ocean, carbon and climate, and he leads the UK's Seacure project, which he's going to talk about with us. Please, Paul. We'll set it in a minute. Dan Bloomfield is the Business Development Manager at University Innovation, Exeter Innovation, taking a lead on nature, recovery, biodiversity and food systems partnerships. Please, Dan, get your seat. You have to be the one after Paul's. Very good. Then we have Torsa Sengupta. Torsa, you with us? Oh, hi, Torsa. A postdoctoral researcher at university, specializing in quaternary environmental geology. Good stuff, that is. Geochemical methods and paleoclimate reconstruction. We'll have a good chat about that later, actually. And then Beccy Mitchell is the CEO and founder of Quanterra Systems. Beccy, please. An Exeter-based company providing site-specific measurement of carbon and water fluxes to support monitoring and optimization of land management practices in nature-based solutions in agriculture. And finally, Iain Hartley. Iain? Hi, Iain. Is Professor of Terrestrial Ecosystem Science at Exeter, and his research focuses on how rates of carbon and nutrient cycling in terrestrial ecosystems are controlled, with a particular emphasis on soil processes. Thank you, panel. We're just waiting for one more, and that's Paul. Can we do that? Here's Paul. Ah, Paul, hi. Come in. There you are. That's all right. That's okay. I've introduced you already. And so what I'd like each of you to do is come up here as for the last session, 5 or so minutes speaking about it, and then we'll open up for discussions with everybody. Please, Paul. Round of applause, please.
All right, sorry about my tardiness there, but I'll crack on. Yeah, so I want to talk to you about Seacure, which we talked about in the previous meeting, but what's essentially happened since then, we were in the kind of planning and design phase, and now we've built and operated for a couple of months our direct ocean carbon removal system. So really learning in great detail about what's going on. Why do we think about the ocean as an opportunity in terms of the carbon removal space? Well, essentially, it's got infinite capacity to either store CO2 or to be a source of CO2 that we can capture and store elsewhere, and then remove CO2 from the atmosphere. That's very theoretical, but a sort of back of the envelope calculation shows that if you just take 1% of the surface ocean water, decarbonize it annually, allow it to refill from the atmosphere as it would do over the following year, remove that carbon, you've dealt with around 12 gigatons of CO2 removal a year. So 1% of the world's surface ocean is an enormous amount of water, but it's a lot less water than we've got. So there's a huge opportunity here. But I'll come back and talk about some of the challenges as to why perhaps that's not the right way to talk about the problem. So the pilot plant we built is around the idea of direct ocean carbon capture or direct ocean carbon removal, where CO2 is really enriched in seawater. It's enriched because when CO2 is absorbed into water, it turns into carbonate and bicarbonate, forms of CO2 that aren't volatile, they don't exchange with the atmosphere. So we've got a starting point with an awful lot of CO2. We take that through the plant and we just separate the carbon dioxide from the water. Trivial-ish. Purify the CO2 and store it. So you're then releasing this decarbonized water back to the ocean, and it's there that it's taking CO2 out of the atmosphere. So I'll talk through the pilot plant and exactly what it does in a moment. But I think it's useful to place this in the context of the sorts of things that other people in this room are working on in terms of the carbon removal space. And really just want to highlight that the ocean is a huge opportunity, but really I think underexplored in this space compared to the land. If we drop down towards the engineered solutions, from a land point of view, we've got DAC, which will be rightly, I think, the focus of most of the conversations here. As it was sold earlier, it's small footprint environmentally and physically, and the cost is the challenge that needs to be resolved there. Bioenergy with carbon capture and storage is very mature already. Enhanced rock weathering, huge potential. When we move to the ocean, we've really got ocean alkalinity enhancement, which has been thought about for a long time and is starting to be applied and tested. And we've got direct ocean capture, what we're talking about here in this talk. When we're looking at direct ocean capture, there are only two people who have built pilot plants, or two groups who have built pilot plants. Captura, a Californian-based startup who are doing some really cool stuff, and us. So it's this huge part of the question that is really extremely kind of light in terms of our level of understanding and level of development that it's received. So, my one sort of takeaway, I think, from this is really that the ocean offers huge opportunities, and we need to perhaps focus a bit more in this area. So how does the pilot plant work? Well, we take the seawater in, as we've discussed, and as I said, we remove the carbon dioxide from the water to then purify it, and ultimately that would be stored. We're venting it back to the atmosphere. We're releasing the decarbonized water. The removal, we've just gone for a very, very simple system, probably similar to what is happening in carb fix. Water raining down, water going in the opposite direction, carbon being taken out extremely efficiently. So 90% of the carbon is removed from that water as it passes through the seawater stripper. So all very straightforward, except before that water has the carbon removed, you've got to acidify it. So you've got to turn all of the non-volatile forms of carbon, bicarbonate and carbonate, into CO2. That happens as soon as the water is at pH 4, which is not a big pH shift in terms of the acidity of that water. That's kind of orange juice, apple juice concentrations rather than anything particularly aggressive. But you've got to generate that acid and base, or you've got to use that acid and base from a very low carbon source. So we're using a bipolar membrane electrodialysis approach, which is taking seawater, or taking water, H2O, and splitting it into H plus and OH minus, the acid and the base. And they're essentially used, as I say, to acidify that water and then neutralize that acid before the water is released, which resets its capacity to hold CO2. So that's sort of 4 of the 5 parts of the process. The final bit is that if you're to do this electrochemical step, we actually need to remove all the calcium and magnesium, or pretty much all of the calcium and magnesium from the water. Otherwise, you get scaling forms, calcium carbonate, magnesium carbonates, hydroxides forming on the membranes in the electrochemical step. But really, the process is as simple as that. Take the water in, remove the calcium and magnesium. We do this by precipitating it out, the electrochemical step, and then the purification step. So we built the pilot plant. We've run it for 2 months to really understand some of the challenges about doing this in the real world environment. And this is taking real seawater in, discharging the decarbonized water. And that's been kind of a huge amount of what we've learned. But the pilot plant itself has only been one of a number of parts of this project. So we've had to be asking the question, what happens when you release decarbonized water back to the ocean? We don't know. That doesn't exist naturally. So we've been trying to start building the evidence base around that. We've been asking and building models and doing field work to test the questions around verification. The carbon dioxide removal is happening downstream of the plant. You can't just say because you've got it in your bottle of gas that the CO2 has been removed. You have to prove that removal. So lots of work to sort of test how that would operate. How feasible is that? We've been working again with the regulators, and really that comes back to the fact that this decarbonized water doesn't exist anywhere else. We're starting building the evidence base and having the conversations with the regulators from the start. And then the last bottom 2 on the right-hand side is we're starting to think about the scalability of this. So where does it work? Where doesn't it work? What is the opportunity for cost reduction here? So just to kind of pull things together, we've learned an awful lot from this process, and I've sort of pulled out a few things that I thought might be relevant to this audience, but I'm very happy to talk for hours to anyone else about all the different things we've learned. So one is that actually scaling this stuff up, the plant works. Building it larger is an engineering problem, or in a more modular state, if that's possible. The break on how quickly this stuff can be scaled is actually, at this stage, the marine impact evidence base. We can't get the permits for the bigger and bigger plants. Rightly, we need to understand what the impact of that is. So that's where the focus in the short term needs to be to allow us to test this as we move through scale. The energetics of this are ultimately pretty similar to electrochemical DAC. Unfortunately, they don't blow direct air capture out of the water. But essentially, you've got a trade-off between trying to push CO2 and absorb it into your solution in electrochemical DAC, or in our situation, pre-treat a bunch of water that comes in. The rest of the process is kind of the same. So I think there's some really nice things that'd be great to test with experts in the direct air capture field to understand, is this something we should be pursuing, or is DAC always going to be better? again, we've done comparisons with electrochemical ocean alkalinity enhancement. We can talk about some of the pros and cons there. The MRV works. It's often the focus of ocean-based approaches. People get very worried, you can't do the MRV. Well, I've been working on ocean carbon removal for the last 20 years or so from the natural state. How does naturally the ocean take up CO2 through the natural cycles? That's really hard because the signal's really small. Here, the signal's quite big. This is a solvable problem. And I'll talk about the challenges in the next slide. I think perhaps the biggest thing is to come back to that global map where we said, well, you just need to process 1% of the world's ocean's surface and you've solved the problem. The challenge actually is that chemically that all works fine. What you're limited by is the flow of water. So you can't just decarbonize the same pool of water. That water has to move away and at least to be away from you for a year or so before it's reabsorbed CO2 and comes back. So when we look in detail at this, you realize that actually the geographical constraints on deployment and the scale you can reach because of that become a challenge that we need to think about much more carefully. And I don't think it's really been discussed in the marine carbon removal sphere. So I'm just going to leave one slide up saying that the next focus, the one thing we didn't do in this project was thinking about the social license for this activity, which again, we think is absolutely critical. I've got a funded piece of work looking at that, but there's loads of other activity. I've highlighted sort of 3 kind of priority areas that we want to kind of really push forward. Now we've got a pilot plant up and running. And if people are interested in collaborating or we can learn from your journey, we'd absolutely love to. So thank you very much.
Thank you, Paul. Great stuff. Next up is Dan Bloomfield. Please, Dan.
Thank you very much. As Martin mentioned, I'm from Exeter Innovation, and Exeter Innovation is the part of the university that builds partnerships with business, seeks to generate impact and basically make all this research stick in the real world. And I wanted to wave a couple of flags. One is that one, the Exeter Innovations flag, and tell a little bit about how we support growth in this area. And also wave the flag for biodiversity and for nature, which is my angle on all of these things. So
I think that's the pop-up we were at as well, just to say.
Say again?
On the bottom right, that's where we were last night. There, yeah. Just to make, sorry, interrupting. I thought that was an important point to make.
I meant that to happen. So very briefly, what do we do at Exeter Innovation? Much of what we do is based on partnership, key partnerships with key stakeholders, of course, and much of what we do is about helping SMEs to grow. So as you can see there, we've worked with over 2,000 businesses on year-on projects worth about £86 million a year in support. And we have our vehicle for doing more business growth and business support, which is Green Future Solutions. And we have colleagues from Green Future Solutions who you are more than welcome to chat to about that. And that's just a little graphic about some of the impact that one of our recent programs in Cornwall has achieved in helping businesses to become more sustainable. But and those are some of the businesses that we've helped, and some of those we've heard about and we'll be hearing about from the panel that's in front of you a little bit more. But they cover the full range of interventions and climate and carbon interventions. But I also wanted to say that all of that work in terms of building relationships with business and sponsoring and creating innovation rests upon research, of course. And there are at least 3 projects there that I wanted to identify or highlight that we aren't talking about elsewhere in this session. So the Add Trees project is an AI-driven project very much geared towards helping the UK government deliver its tree planting objectives. The Future Fibres Network is a project entirely about decarbonising an entire industry, effectively. The clothing and fashion industry, the textile industry. We also have a whole series of other projects going on that look very much at the social and cultural aspects of land use decision making, because many of the actual things that we're talking about here rest ultimately upon changing the use of land and building things and doing things on land. And so understanding the historical and the cultural aspects of those processes are really key to understanding how we can bring around the changes that we want to see. But I also wanted to say, and perhaps sort of provide a little bit of a challenge about nature, because nature and biodiversity is, as I said before, my angle on all of this. If you treat the biosphere as a means just for managing waste carbon, you can end up with nature-based solutions that do very little to address that existential threat to humanity that is biodiversity loss, or in fact even sort of contribute to and accelerate its negative impacts. And I think that's a really important point. Nature biodiversity loss, I would say, is the somehow less glamorous and weirdly less funded existential threat to humanity, but it is actually the most urgent one. And I would say that if you end up with a 300 or whatever parts per million target, and you keep climate change down to 1.5 degrees, you might think that's a win. But if you do it at the massive biodiversity loss, it's just a loss. That's no result. So I'm very interested in understanding and hearing about projects where we are investing in nature-based solutions that simultaneously contribute to the strategic objectives of biodiversity recovery, which are not always about planting large amounts of eucalyptus trees, and they're not always about or fir trees. They're often more integrated solutions, such as, for example, we're doing some interesting work around seagrass, conservation of seagrass growing, where some of that carbon through sediment layering can be sequestered away for much longer timescales, and also things that we can do around peatland restoration, for example, that simultaneously enhance the loss of biodiversity or reverse the loss of biodiversity, as well as achieving some of those carbon targets. So I would just encourage everybody within this coalition, when you're thinking about nature-based solutions, those kinds of regenerative agriculture and food interventions are really going to be absolutely critical. I do think that climate innovators need to be thinking about alternative proteins. They need to be thinking about agricultural practices like no tillage that keep that carbon in the soil and so forth. I'm basically just waving a flag for nature and saying, please don't forget nature, because otherwise we'll end up with a highly depleted world, wonderful temperature, but destroyed nature. I don't want that solution. I'm sure no one else does either. So that's me. And please do talk to us and my colleagues from Exeter Innovation if you'd like to know a little bit more about how we can support this change and this switch.
Thank you, Dan.
Oh, sorry. Oh. I think there might be one more slide. I was just going to say that you have to be very creative about finding the funding solutions to get some of these things happening. And so quite often they involve working with farmers, and quite often they involve working with strange sources of money, such as the European Space Agency. There are current open calls or imminent calls which would relate to some of the objectives of this conference. And so again, talk to us if you'd like to know a bit more.
Thank you, Dan. Wonderful. Thank you. Next up is Torsa Sengupta. Please, Torsa.
Hi. So like after all of this talking about like carbon captures and all, this is a project that I'm going to just present, which is talking about rather most natural solution, rather what not to do and just preserve what is naturally carbon sequestered in the sediments, mainly in the marine sediments of the continental shelf sediments. So this is a project which kind of focuses on the carbon, that's like the organic matter that could be plant remains, animal remains, and that's sequestered naturally in the marine sediments. And it focuses on there are three key questions of this project that focuses how this carbon stores had formed, when they deform, and how much carbon stored naturally in there. And then what are the disturbances that we are doing into that sediment? So it's in this continental shelf sediments that can actually host more than 200 gigaton of carbon that's naturally sequestered there, like in these plant forms and the organic matters. But like the bottom disturbances, like trawling activities, like fishing, that and dredging by ships, that kind of resuspended those sediments and exposes those carbon that's naturally sequestered in, like they're just exposing this carbon for natural oxidation that was not being oxidized in a condition where it would not be disturbed. But when you disturb the sediments, it just locked up the sediments and exposes this organic matter and exposes it to oxygen exposure, which will then oxidize this carbon to carbon dioxides, which increase the carbon dioxides of the ocean, and that can further goes into atmosphere for this and probably aiding in this carbon emissions and all the climate change that we are facing. So the key question is the formation, which deals with where is the carbon, how much is the carbon, and to understand where did it came from and how old is that carbon and what is the type of the carbon it is. And then we also are focusing on what happens to this carbon when this gets disturbed, whether they change into carbon dioxide, what happens to the ocean chemistry around those sediment interface. And the other question that we are also looking, so if you have heard about the marine protected areas, that mainly focuses on to increase the biodiversity of those regions. If we focuses on these marine protected areas where there were relatively less bottom disturbances, whether we are able to fix this carbon issues, whether we are able to do something like going backwards and able to store this, like use this carbon stores again. So, and all these are like interrelated by some modeling and experiments that we are doing in this project. And so all these projects are related to, if we know where are the carbon, and then we want to measure what are the disturbances in there and how much carbon is oxidized. And if we are thinking about the marine protected area, which is mainly be resolved in the forms of biodiversity, whether that marine protected area is also able to recover this carbon or whether that is much more doing the biodiversity protection. So if that's the case, then should we increase or like should we in the future, should we take this carbon capture, like not the carbon capture, but the natural solution of this carbon stores into consideration when we focuses on the marine protected area in future? So it's basically rethinking like whether this biodiversity protection is efficient in resolving the climate change issues from the carbon dioxide emissions as well. So for today, I mainly work on the geological or the sedimentological aspect of this project. So we want to find what is the carbon, this kind of question. And this is we are still waiting for the infographics for a much more fancy diagram, but this is a very initial diagram that I made, how the carbon goes into these sediments, what are the sources. So there are like rivers and other terrestrial things that brings the carbon from the terrestrial reservoirs to this continental shelf. That's continental shelf are the shallower, like relatively shallower parts of the marine realm. And then there are some marine productivity. That means like all the marine plants and all that uses carbon dioxide for the photosynthesis and then capture those carbons. So those plant remains, when they die, they go down and form the carbon stores from the organic and form the organic matter in the sea base from the carbon stores. Not only that, so there are some small fishes and all who kind of feeds on this marine planktons and all. They also come up to the surface, like have this carbon ingested, and then then their body remains as well as their feces that forms the crux of the organic matrix in the sediment surface. And those are the carbon stores, that like the whole carbon in the sediments of the continental shelf. Now, so this is a continuous process. Like there would be like sediments going on and settling down. So like the top sediments at one point of time, depending upon the rate of the sediment input in particular area, in different areas, that would be different. That will go below the surface, and there will be new sediments in the top of those sediments. That kind of essentially locks away this organic matter from the oxygen exposures. So there is this thing where the geology comes in. What is the sedimentation rate in that particular area, and how the organic matter that forms in the sediment matrix and the top will go down and essentially lock them away from any disturbances. And when I say disturbances, that could be trawling. If you could just see that, like in this, the trawling nets, that kind of lofts away like 30 to 40 centimeters of depth it could go, and then it lofts the sediments away and put the organic matter into the to be oxidized. So that's how we lose the organic matter and the carbon in the organic matter, and that will generate the CO2 in the water that will ultimately go to the atmosphere by acid exchange. So there is a lot of other things going on. So how are the ocean circulations? What are the type of the organic matter that is coming in? That kind of give the total organic matter or the total carbon stores, like that put the number in the carbon stores in these sediments. So in a very layman term, I would say, like, if there is a lower energy, there would be much more muddy sediments, which can have much more organic matter. So if there is a little bit higher energy, like much more ocean circulation, then there would be much more coarser sediments, which will have less organic matter in that. So in our project, we try to find out what are the mud hotspots where the carbon could be maximum. And not only that, when I say the organic matter, that could be like different kind of organic matter. Some organic matter, even if they are exposed to oxygen, will be resistant for oxidation. That's in their composition. And there would be some organic matter which would be much more vulnerable to oxidation. So it's also important to understand which part of this sea have what kind of organic matter, and that depends on, again, the sources of the organic matter, the composition of the organic matter. So I mainly focuses on this, what are the type of the organic matter, and say in a mud basin, so we focuses on what's the source and what's the type of the organic matter that's deposited in. So that's how its importance of the geology and the sedimentological history of a particular mud basins come into the picture. So when I say, I'll just go back, and when I say, just if you could just see, so there would be an organic matter in here, or the sediment in here that will get buried with time below the zone of disturbances. And so if there is a slow burial, like there would be not that much of input, that will go for that will stay into this zone of disturbance for a longer time, and that kind of increases its vulnerability. Whereas in one situation, if there is much more high sedimentation rate, that means a high input from the terrestrial as well as the marine sediments, so that will quickly sequester below this zone of disturbances, essentially locking away the carbon or the organic matter from the disturbances, the anthropogenic disturbances. And when I say this comes into picture, the type of the organic matter comes into this picture. So if there is a much more easily degradable organic matter, and also a very slower burial, so those areas would be much more prone to emit CO2 if they are disturbed. So that is the reason we want to figure out what are the type of the organic matter. So there are several ways where this organic matter type has been resolved before. So it's mainly, when I say vulnerable organic matter, that's called a labile. So they do different kind of method that has already been used before by rising different temperatures and see at different temperature, different organic matter would decompose, and that temperature boundary said, okay, this organic matter would be much more vulnerable, and the organic matter that decompose into a higher temperature would be less vulnerable. We are also now, there are some other methods of doing that as well, which we will be doing in the next couple of months of this project. This comes into our consideration because essentially what we are doing, we are oxidizing the sediments. So there are a very typical kind of understanding this vulnerability in soil science where they oxidize the sediment by using another oxidant, any kind of oxidant. So that we will be doing in our project in the next couple of weeks, next couple of months, to see if we chemically oxidize those sediments, which sediments would be much more vulnerable releasing carbon dioxide and which will be less vulnerable, and so that we would kind of locate which areas are much more vulnerable, and that probably will incorporate into the future decision of making a marine protected area, not only about thinking about the biodiversity, but also thinking about it as a natural carbon stores and not to disturb those carbon stores. I'll just quickly go here, just to see. So we have already done a very preliminary study, and where we see in one kind of area where if you can see the sedimentation rate is pretty slow, and because it is pretty slow, the organic matter is naturally degraded. So there is no difference in between. If we go down, there is no difference between the vulnerable and the more resistant organic matter. But whereas we will be using this same method in another area where there could be the organic matter or the sediment deposition rate is very fast. So probably there are still some organic matter that has been locked away, will have this labile or the much more vulnerable organic matter that has not been naturally degraded, rather essentially locked away from the natural degradation. So that's where we will, but that's also a fishing ground. That's also from a fishing ground. So we will do this analysis to check whether they are still able to release CO2 if the trawling goes on these areas.
Okay.
Thank you.
Thank you, Torsa. Wonderful. Thanks very much. Next up is Beccy Mitchell. Beccy.
Hello. So I'm not going to talk about how we capture carbon. I'm going to talk about how we know we're continuing to do the right thing. So I'm also going to talk specifically about nature-based solutions rather than more widely kind of technically oriented ones, but there is an increasing overlap between those two. So we're a spin-out from the University of Exeter. We're 4 years old now. We actually started as a research project, which I think was before Arizona State and Exeter had a formal relationship, but actually involved a professor of practice at Arizona State, my co-founders Tim and Rob, and it was focusing on how to undertake measurement in a scenario where the Arizona State University professor of practice was looking at storytelling associated with regenerative agriculture. So essentially, nature-based solutions offer us plenty of opportunity, but they also offer some unique challenges compared with more of the permanent solutions. Somebody mentioned earlier that they're kind of generally carbon sequestration in nature is temporary. It's part of a cycle rather than being financing for carbon projects, unless you can demonstrate it's having an impact. So we work particularly in scenarios where people are trying to capture carbon within soil, or at least that's how we started. That's partly because it's more challenging from a measurement perspective than when you're looking at the carbon accrual within above ground biomass. But increasingly, people are recognizing the complexity of that system also means that the interactions between the soil and the biomass, or the land and the atmosphere, drive other challenges that mean that we aren't as confident as we could be about the scale of uptake by, for example, tree planting in certain environments. But for soil carbon, it's particularly challenging. And the reason is there's sort of three core measurement technologies that are used widely at the moment. The first of those is soil sampling, where people take a sample of soil, they measure how much carbon's in it effectively by burning it in most scenarios. And then they wait for a long time because soil carbon accrues quite slowly, and detecting a small change in a large mass is pretty challenging. And so you wait sort of 5, maybe 10 years, and you measure it again, and then you detect the difference between the two. But that's kind of like checking your bank balance today and then waiting again to do it again in 10 years' time and hoping that you've got more. Unless you actually understand what's happening on a kind of granular basis, it's really hard to manage. It's also got complexity in when it comes to scaling, because you need to take quite a lot of soil samples at any given site to actually get a robust understanding of what's actually happening. So people then have started to try and use remote sensing, where you look at things like LiDAR or satellite imagery to understand what's happening above the surface and to try and infer from that what might be happening below the surface. And that has the advantage of being globally scalable. It's obviously much easier to get a kind of a large scale understanding of what might be happening, but it has the disadvantage of also being challenging because you are inferring what might be happening below the surface based on what's happening above. And as a consequence, you have uncertainties associated with that interpretation. The third method, which is obviously increasingly exciting for people, but also has the danger of being buzzwordy, is to be able to use models. So AI, biogeochemical, process-oriented models. And they have the advantage of being quite globally scalable, that they can be deployed at wide scale. You can run them quite frequently, but they have the classic challenge: if you put rubbish into them, you get rubbish out. And so calibrating and validating those models is very challenging. What Rob and Tim were looking at some time ago now, about 2018, was using a technology called eddy covariance, which has been around for about 50 years or so and has been used widely, but it's historically been extremely expensive to deploy. The components of equipment required are very costly. It requires a huge amount of expertise to actually implement it. And as a consequence, has not been deployed widely outside of kind of domains where there are wealthy universities, essentially. What it does is take our understanding of atmospheric physics and our understanding of atmospheric transport to measure at very high frequency parcels of air being transported through the atmosphere. Those parcels of air, we measure the speed and direction of those parcels of air and the carbon dioxide concentration within them. And by using some complicated maths, you can essentially take all those high resolution measurements and you can determine on a half-hourly basis how much carbon has been emitted by the ecosystem and how much carbon is being captured by the ecosystem. So you get a very high temporal resolution understanding of what carbon exchange is happening across the ecosystem. And you have that around a tower, which you deploy. And as the wind changes direction, I think I'm the second person to say that today, which is not a usual occurrence. As the wind changes direction, the wind blows from different positions around the tower, which in turn means that you're measuring different aspects of the tower, which means you get spatial interpretation. So unlike soil cut sampling, where you only get the one sample from the one point of where you've taken that sample, in this particular case, you get aggregated over a 4 to 10 hectare area, usually when you're looking at towers above grassland or cropland like we deploy. If you were to deploy very tall towers over things like forest, you'd be looking over a larger area still. So you end up with a position where you've got half-hourly measures of carbon being exchanged across that ecosystem at a relatively high, so high temporal scale, but also a relatively large spatial scale. And within academic circles, ecological and ecosystem science, it's been kind of known as a gold standard for some years. But as I said, it's expensive to deploy and complicated to run. So Rob and Tim had been looking at how to deploy a more effective, from a cost perspective, version of that technology. That led us through various stages to come up with the idea of setting up a spin-out, which is Quanterra. And what we do is take the technology that Rob and Tim were putting together, which is more affordable actual hardware, and we couple that with basically software processing that overcomes some of the weaknesses of using cheaper hardware, and couple that with an as a service business model, so that we can effectively do all the complex maths and the like that are involved in coming up with the answers, do all the challenges associated with logistics, which require the deployment of these devices, and address the spatial and cost challenges associated with the technology used in an academic domain. So we brought that business to light because in practice, if you're trying to do things like soil restoration projects or cropping, regenerative agriculture projects, or even restoration projects for peatland or various other ecosystems where carbon has been lost from the soil through our industrial practices or generally human interactions with the land, you need to be able to measure the technology, use measurement technology to establish, are we making headway in addressing some of those weaknesses through our new approaches? And some of the ones that are coming up more recently are some of the things that we've mentioned today. So soil amendments, whether that be rock dust or seed coatings that might reduce the amount of stress on a plant system such that you can grow them more effectively. There's various other things too, but those things need measuring at scale in order to be financed, but also in order to establish whether you can do things like offsetting, insetting, Scope 3 emissions monitoring for part of food supply chain, timber supply chain, and the like. So we've now deployed, I can't add those numbers up quickly in my head, but just over 120 systems around the world, predominantly in the USA. The land masses are large and the money is reasonable in terms of accessibility. But our aspiration is to make sure that this is also in line with the fairness and justice points, deployable in areas where there are various challenges associated with monetary aspects of this, but also have huge potential to be part of the solution when it comes to monetizing nature-based solutions. You can see in the pictures here that they represent a variety of ecosystem types, predominantly within the agricultural supply chain, grazing, croplands, some peatland restoration projects, a rewilding project. And you can see that the systems themselves, we've endeavoured to make them as unobtrusive as possible, but part of our future direction is to try and shrink down some of that footprint so that they can be more deployable within an agricultural setting without causing challenge to the agricultural operations. And in line with everybody else, this isn't a silver bullet. Part of what's good about measurement technologies is that they all bring their place. So those three that I mentioned earlier, we don't dismiss those. We think that they're part of the solution alongside eddy covariance. What we're hoping to be in a position of is work with both commercial and academic collaborators to be able to integrate the continuous monitoring provided by our solution with intermittent spatial data provided by remote sensing, point data provided by things like stock sampling, and then AI biogeochemical models so that we can come up with something that is more akin to a real-time ecosystem scale representation of how our landscapes are responding to the solutions that we're trying to implement. That's my lot.
Wonderful. Thank you, Beccy. Thank you. And last person on our panel is Iain Hartley. Iain, please.
Hi, so I'm Professor Iain Hartley. I'm based here in the Geography Department. And what I was going to talk to you today about some approaches and technologies that we're using to try and understand and evaluate different land-based climate change mitigation techniques. Some of this introduction has already been given, so I'll go through it reasonably quickly. Obviously, there's 8.2 billion people on the planet now, and we need to feed them all. Agriculture is not an industry we can do without, but about a quarter of all the climate warming associated with greenhouse gas emissions comes from agriculture or land use change. So reducing those emissions is important. Since intensive agriculture was developed, we've lost perhaps over 100 billion tons of carbon from the world's soils. And in the Paris Agreement, it was recognized that getting back a substantial proportion of that carbon could be really important in terms of climate change mitigation. But agricultural systems are also major sources of methane and nitrous oxide. In areas where we don't have deforestation, it's actually those greenhouse gases which are perhaps the biggest part of agricultural's impact on climate change. So reducing those emissions is also essential in terms of sustainability. So as Beccy just suggested, there's a lot of investment in projects and programs that aim to either promote carbon sequestration in soils and or reduce or avoid the emissions of nitrous oxide and methane. Evaluating which options are best and also verifying whether the carbon uptake has taken place is not that straightforward. So in terms of a couple of challenges, Beccy's already emphasized the challenge of detecting a small change in the big number when we're thinking about soil organic matter and the potential for eddy covariance in that space. So I won't go through that again. But if we think that detecting carbon storage, changing carbon storage is difficult, completing full greenhouse gas budgets is even more challenging. So for something like nitrous oxide, it's a powerful greenhouse gas, but it's not abundant greenhouse gas. So the equipment that we need to measure nitrous oxide concentrations is often very expensive. Nitrous oxide is also a very difficult gas to measure because its fluxes are incredibly temporally and spatially variable. It tends to be associated with hotspots or episodic events such as rainfall. And for that reason, we can spend a lot of money on our analyzers, put a lot of time into those measurements, and we still have quite high uncertainty in terms of nitrous oxide, at least in the field. Now, I introduced those two issues separately, but actually they should be intrinsically linked. It's highly likely that an approach that promotes carbon sequestration in soils will also have an impact on the emissions of nitrous oxide and methane. So we cannot be fully sure what the impact of our intervention has been unless we can complete those budgets as well. Now, for most project budgets, in terms of financial budgets, it's quite hard to resolve those issues. So some of the things that we've been doing has been trying to set up simulations in the laboratory that allows us to evaluate some of those different interventions in more detail. So we've been developing continuous isotopic labeling that allows us to much more precisely quantify rates of carbon storage in soils or carbon sequestration in soils, at the same time linked to high frequency measurements of those greenhouse gases. So how do we do that? Well, we put basically more of the heavy isotope 13C into the air inside bespoke chambers, and we measure that heavy carbon as it's taken up by the plants and moves into the soils. And that allows us to precisely and quickly quantify carbon sequestration. Now, the requirement for that is we have to have very constant isotopic labeling. So that graph up in the top left over there shows a concentration or an isotopic signature of 500 per mil, and it shows it over a course of a 24-hour cycle. But the data that underpin that is not data from one day, that's data from 6 months. So we're able to precisely and continuously label at 500 parts, 500 per mil, which gives us a very strong difference between the new and the old carbon in our system. And although the photograph's not particularly very clear, you can perhaps see there's lots and lots of different lines going from those systems, and that's where we're measuring our greenhouse gas emissions from very high frequency. This experiment is from some of Needham Friggan's work, and we were looking at grassland systems there. We've now developed bigger systems where we can take crops all the way through to cereal production. Why does this high frequency, or why does this high isotopic signature matter? Well, previous experiments removed CO2 from the air and replaced it with fossil fuel CO2, for example, to allow that difference in isotopic signature between the old and new carbon. There you're taking 13C out of the system and can perhaps get to maybe minus 50 per mil, which is a good difference. But even at 5% new carbon, we probably on every experimental system have an 80% uncertainty in the rate of carbon sequestration. When we go up to 500, when we go up to 500, over here, we can get down at 5% carbon to an uncertainty of just 5%. At 2% new organic matter, we probably have an uncertainty of around 10%. At 1% new organic matter, we have an uncertainty of only about 25%. And when we replicate that, we can get those down further. So that means with that isotopic information, we can quantify rates of carbon sequestration really rapidly. So instead of needing 5 years or 10 years to detect the carbon uptake, we can do that in the course of a 6 or 9 month experiment. And that allows us to screen lots of different interventions together and work out which have the greatest potential to promote carbon sequestration. At the same time, we have our high frequency measurements of our greenhouse gas fluxes. And that allows us to make sure that those carbon sequestration numbers are not at the expense of greater greenhouse gas emissions. And ideally find solutions where we both reduce the greenhouse gas fluxes of methane, nitrous oxide, and we also promote carbon sequestration. So this is a challenging area. We're not suggesting that we can replicate every aspect of agricultural systems in a lab, but by using this continuous isotopic labeling and high frequency greenhouse gas emissions measurements of fluxes, we can rapidly quantify rates of new carbon formation and sequestration and ensure that that's not at the expense of any adverse effects. When we do that, we can screen lots of different interventions. Maybe we've taken interest in a particular soil type, particular crop type. Maybe you have a product, a soil amendment that you want to use, and you want to know what its overall impacts might be in this field. And by doing those short-term experiments in advance of maybe larger field trials, the aim is that we can avoid investments in those experiments or those managements that take 5-10 years, and we find at the end of them they didn't do everything that they needed to do. So that's the technology that we've been developing in this space here in Exeter.
Thank you very much. Thank you. Okay, now we have time for questions to our panel from all 5 speakers. Thank you ever so much, Paul, Dan, Torsa, Beccy, and Iain for that. Yeah, please, Walter. Hang on, I've got the both of you mic.
Walter Merida from UBC in Vancouver, and I have a question for Iain. You talked about nitrous oxide and CO2. What about methane? Can you do the same kind of work as quickly and as effectively with methane?
Yes, methane is easy. Nitrous oxide is the hardest, CO2 is the easiest, and methane's in the middle. So the only issue with methane is obviously we can't put a cow in our chamber. So we're not going to tell you about methane from livestock. And also we need to work with very large experimental units, because when we work with methane, it's because of anaerobic conditions developing in the soils. You have to have a big system before you reduce oxygen diffusion rates enough. So you often need very, very big experimental units, which obviously reduces your replication. But yes, we could do the same. An ideal size is probably 60 to 80 centimeters just for a single unit. If you can get up to a meter, then that very much gives you the system that will simulate accurately oxygen diffusion rates. If you're working in the systems that we might do when we're mainly looking at nitrification and CO2 production in aerobic systems, we can do those in 20 centimeters or 30 centimeter systems. So for methane, you need to go to bigger units. If you're simulating, say, rice agriculture or something like that, you need a much bigger system. That would be very heavy, and you need to make sure that you're not overloading your shelves with that. But yes, you know, obviously, you can think of a bulk density of about 1.5 when it's fully water saturated, these systems. So you multiply that up by the depth and the size of your system. So yes, it does get heavy, and you need a lot of soil.
Okay. Richard Profit from the Cool Farm Alliance. This is to Beccy and Iain. Really useful research and really helpful for informing the models that are out there. Question for scale, what's the sort of planning figure from a cost perspective to deploy that at scale for both those technologies?
This is one of those terrible commercial responses of it depends, isn't it? We tend to try and operate in ecosystems where we can be reasonably clear about that. But if you operate in more complex ones, it's harder. So in a grazing system in the US, we would generally be looking at around about $15,000 per tower per year. That's still quite expensive, and one of our aspirations is to drive that down, and it really does depend on the nature of the supply chain as to whether it's affordable or not. If you tried and do the same thing in something like a rainforest, obviously you'd be looking at a much bigger tower, which has much more cost associated with it. And so the complexities of the ecosystem make a big difference.
I guess Dan can speak more to the cost of doing university research, but in terms of just the cost of running our experiments, it depends a little bit on what your key aim is. So if we want to be able to detect the carbon sequestration really rapidly, we go to the higher and higher isotopic labeling. So to do a 6-month experiment, we're probably talking about something between £5,000 and £10,000 for the CO2 costs, just to make sure that we can get a high enough label. If the greenhouse gas monitoring is more important than the carbon sequestration, then that's you know, a continuous cost. But for the consumables, to do the labeling so that we get a high degree of confidence in the carbon sequestration, then we're looking at about £5,000 to £10,000 for the carbon dioxide that we use, the heavily enriched 13C.
Kyle Dada from Teneo in the US. This is a question for Beccy, also on the painfully commercial practical side of this. So I've got 2 questions. The first is your technique accepted by any US regulatory authorities in terms of the quantification? That is it an accepted technique? And then secondly, building on that question, for your towers, how many towers do you need per, say, every 100 hectares, or however you look at it spatially? What's the relationship on, say, a grazing system, a simple system, so we get a sense of cost and scale?
So in terms of the scale, it really depends on the ecosystem itself. So a large grazing system in Wyoming, for example, where you might have tens of thousands of hectares of land that are largely the same as each other, and it's kind of quite a homogeneous landscape, you might only need 1 tower and a whole variety of model capability to upscale to a much larger scale. If you're in a sort of a much more small scale pasture in Mississippi, where there's huge variety in the pastures, many more treescapes and things like that, then you might need a few towers in order to couple it together. It also depends on the level of certainty you want. So from an ecosystem science perspective, people have historically made sort of great sweeping judgments about an ecosystem's performance based on a single tower for huge landscapes. But that's because they were trying to understand a kind of broad top level understanding what was happening to the ecosystem. If you really wanted to have a degree of certainty that you might need for something like a carbon credit market, then you might need more. So one of the things that we do, so the price I mentioned is based on a full service, which incorporates doing the modeling of where the towers would be deployed, all the way through to providing the half-hour data at the end of the processing. And one of the things we do as that early step is to try and take ALM's files or similar to say, okay, let's look at your project and try and understand what would look like an effective deployment in the context of whether it's a homogeneous or heterogeneous landscape. In terms of regulation, much more complicated. We're working on a couple of solar agrivoltaics projects where they're undertaking grazing under solar farms to work with a carbon credit verification agency to put together a protocol that works for that particular technology. Eddy covariance as a technology is only just becoming accepted as a replacement for things like the classic methods of using soil sampling. And one of the challenges there is that people have historically come to terms with the idea of soil sampling being a ground truth. And the reality is that there's not really any such thing as ground truth, which is why we come to this kind of conclusion at the end of the slides there that highlight the necessity to bring together all of these different data sets. So it's a moving journey at the moment. From a supply chain management perspective, though, so if you're looking at scope 3 reporting, it's less well regulated than the carbon offsetting community. So for things like food supply chain or timber supply chain or materials supply chain for things like cotton, then it's got potential to be used in those sort of settings. And the other thing I'm going to say is actually going back to the previous question, which is eddy covariance as a technology theoretically can apply to various other gases too. So methane is widely used, but the sensors for that are very expensive. And one of the technologies we're exploring at the moment are the cheaper sensors to see if we can start to integrate CO2 and methane so that we can use them widely in grazing systems. N2O much more complicated again for some of the reasons that Iain's mentioned, as well as the fact that the sensors are power hungry as well as expensive.
Okay, I've got a question for Torsa. We're moving on to some of the other speakers because it was fantastic stuff, right? And there's other things. Torsa, I was interested in the disturbance you have to the marine, the ocean floor, the seabed. Is there a time dependency on when that disturbance happened? So are we talking like recent, like a few months ago, or are we talking maybe some years ago, or even we're talking 50 years, 100 years, or multiple disturbances? What's the sort of time frame over which we're thinking about these observations?
I think that's another aspect we are also looking. So yes, there are recent disturbances. So we are also in another work package of our project, we are looking, so if there is a marine protected area, say for 50 years, whether that is capable of recovering the carbon lost or not, or it is like probably what that is lost is to be typical saying like what is lost from the sediment is lost, but whether you protect that area, there will be much more conservation and the biodiversity restoration. Will that again help having much more carbon sequestration on those marine protected areas or not? But it includes recent disturbances as well as the past disturbances as well.
Okay, got it. Yeah, thank you. Any questions on that at all, please?
My name's Allison with Prance Earth News. I think it's fascinating. The ocean covers so much of the earth, and I feel that what you're doing, surveying it for the carbon, is a bit overlooked. I'm just learning about it now, even though I have some software tools that help measure acidification and MPAs and habitat and such. It seems to be a bit of an analogy with permafrost. And the Woodwell Climate Foundation is doing research in permafrost that when it melts, it's going to be so drastic. And it's so unknown, but I mean, it's not well known. So I think what you're doing is really important, more than people realize, except for the marine scientists. And I'm just wondering, what will it take to really model the entire ocean? I mean, I know that you can't do that, but.
Thank you for the question. Not entire the ocean. That's what we are doing, as like modeling all the currents and everywhere, and to find what could be the hotspot for the carbon storage. So, like putting the sedimentological knowledge from where could be the carbon storage and where those sediments could be deposited in the ocean floor, and then getting sediments from there, like, and doing experiments whether like our model is validating or not. So that's what we are doing. And when you say like, yes, there are other areas to explore as well. So it's just the 3% is like it's explored, it's like it's protected, is only the 3% of the ocean. So it's not possible, obviously, with some model to have for the overall ocean. But for now, this focuses only on the continental shelves as of now. But yes, probably in recent future, we are also thinking of if the permafrost melts, what are the organic carbon that it could probably give away to this continental shelf, as well as what are the roles of the large rivers and all that it could transport the terrestrial organic matter into the continental shelves and even in the deep seas as well. So what could be the potential for those areas for this natural carbon storage solution kind of thing? So, or again, coming back, what would be the composition of those organic matter that's already been sequestered below the permafrost or by the river or the terrestrial, whether that would be much more vulnerable to the disturbances or not?
Wonderful. Thank you. Paul, I've got a question for you as well. So the Siegert experiment is going on, and you mentioned a lot of detail about how it's been set up and some of the obstacles and issues around it, very open about that. If you had an ideal location to deploy, where would it be? What would it look like to minimize all those things?
Yeah, so I mean, the ideal oceanographically, the ideal location is interestingly kind of actually around the North Sea, and so we're in a pretty good location. So what you need is the water to stay in contact with the atmosphere for a good few months, ideally over a year after you release it, and the North Sea does that. The challenge there is how big you can get. So as I was sort of saying, the pool of water needs to move out, out from where you are. So kind of as a sort of thought experiment, we sort of said, well, what does a gigaton removal plant look like? And actually you have to decarbonize the mixed layer, so the kind of the upper part of the whole of the Gulf Stream pretty much continuously to be removing about a gigaton of CO2 a year. So there are places with very fast flows of water, but you're ultimately limited by this. So what that then pushes you towards, what does it look like? It's sort of distributed removal, which fits with the modularity idea, but presents challenges in terms of how you concentrate that CO2 and store it.
So a totally naive question, right? Which I never mind asking, by the way. Could you fit a sort of modular system onto container ships? The thousands and thousands of them that are all around the world at the moment. Is that a sort of possible route for this?
It's possible, although one of our biggest challenges is decarbonising container ships. So to produce the additional energy required to run these, it's not obvious how you would do that. But yeah, that sort of approach, distributing them, along coastlines or offshore as well, could certainly work.
Yeah, wonderful. Any questions on this? Yeah, loads. At the back. Sorry, my roving mic's coming. Seconds.
Thanks, Paul. I'm Chris Pearce from the National Oceanography Centre. I just want to firstly highlight what a great job you and the CQR team have done, because this is to date the only marine CDR field trial operating in the UK. And just building on that, I was wondering if you could kind of comment on the challenges of running this type of trial, this pilot study, and getting that in situ data, and whether you feel that's been made easier because you've been working through the University of Exeter relative to some of the pilot or commercially led studies that we've had, and kind of what challenges you've faced in getting this up and running.
Yeah, that's a good question. There's infinite challenges, as there are with anything done in the real environment. I think it's coming to your point about doing it versus from a university versus a startup. I think is an important one. And there are two situations where an engineered carbon dioxide removal activity is attempted to be trialled in the UK, ours and Planetary Technologies, who many people might know from their work in Canada, but also tried to do a trial in the UK, and it essentially hit a brick wall and they've given up. So I think doing it, the kind of clarity around the incentives, when you're working in a university environment, help that public discourse. Whereas if you're doing it from a sort of profit motive, I think that conversation starts off in a very different place. So I think that's really important. But the broader challenge is, the regulatory framework is flexible in the UK, but it's very strict. Now that's good and bad, so it does slow things down and adds risk to doing these things, and probably is why a lot of startups wouldn't come back to the UK, because it took an awfully long time for Planetary to get sort of regulatory approval. So yeah, we could talk about all sorts of challenges, but yeah, those are probably the big ones.
Wonderful.
Can I just come in on that? I mean, just to say that a university is it's an expensive place to get things done. We're not enormously competitive against the private sector, but we are very good at modulating and managing risk for these sorts of innovations and these developments. So, which is why to try and sort of square that circle, we've tried at Exeter to become much more agile with our business development programs, and hence the Green Future Solutions vehicle. So we're heading in the right direction.
Orison Horv from the Smithsonian Tropical Research Institute in Panama. Paul, I have a question for you. Our institute works a lot on biodiversity in the tropics. In thinking about decarbonization of water and the impact, for example, in marine ecosystem, particularly in the tropics on coral reef, is there any thoughts on how the work that you're doing with Siegert could couple with scientists associated that are working with the impact of carbon in those marine ecosystems?
Yeah, absolutely. So I guess when you decarbonize water, you remove the acid from the water or reduce the acidity. So in some ways, you're countering ocean acidification. I guess that's where the sort of question comes from. I think we need to be a little bit cautious when we're talking about this, because you release high pH decarbonized water from a point source, if you're doing something like what we're doing, and it dilutes spatially, and at some point it will be offsetting ocean acidification, and then sometime soon after that it'll be so dilute it's not doing much useful. That's not to say that actually point source decarbonisation is not really valuable. So there's certain ecosystems, certain locations where, locally for some spawning ground or, shell fisheries or whatever, it might be really valuable to have that. So I think there are really important questions to explore there. I worry a little bit about that being the gateway to really large scale operation, because it doesn't, the sort of scales don't really match up, I don't think, in terms of answering carbon removal at scale and dealing with those specific ecosystems at small scales.
One more question.
Paul, you're working on an inorganic approach to CDR, with alkalinity addition, but there's a lot of different techniques being proposed. Some of them organic, sort of everything from sort of taking sargassum from the Caribbean and burying it deep in the Atlantic Ocean to putting iron in the ocean and all kinds of things. What do you see as the balance of risks for these things, and what do we need? What should be the first step we take on all of this stuff?
Yeah, so the simplest approach is just to take the carbon back out. So that's the approach we're doing. It's the least kind of impactful approach, I suppose. The next simplest is, to chemically allow the water to hold more CO2, but not mess with the nutrients, not mess with the biological components of the system. So that's ocean alkalinity enhancement. And then I think progressively, as you go through more biological routes, the question just gets more and more complicated. So you're starting to have to track nutrients, you're starting to have to track, larval stages of organisms, if they're kind of moving around. And you get to a point where I think the verification becomes extraordinarily challenging. But there may well be lots of co-benefits. There might be huge biodiversity gains associated with at least small scale restoration of ecosystems. So I think perhaps I don't think the scalability is there in the natural approaches, but I think the co-benefits are there, and they can be there. You could do monocultures of sargassum, which probably would be a great idea. But I think the questions become actually a lot more complicated when you move from the engineered sort of abiotic, the chemical approaches, into the biological approaches.
Time for another question. I've got one more question.
I would just say that the very first step is to do proper biological assessments before the intervention, and proper biodiversity assessments, because that isn't what happens. It's not the first thing that people think of. They just assume that something that's going to help the climate will help biodiversity. Not true. And so that's the first step. Invest in some proper monitoring.
Great stuff. So, Dan, I've got a question for you. And so I was in Westminster a couple of weeks ago speaking with Chris Bryant, who's the Minister for Data and Information or something like that. And it was all about the space sector that's in Cornwall. Cornwall has a space launch facility, by the way. It's not launched anything successfully yet, but it is certified as a space launch facility. And it has the Goonhilly Earth Station. Who's heard of the Goonhilly Earth Station? One or two? Who's heard of the Hitchhiker's Guide to the Galaxy? Everyone, right? Page 7 of the Hitchhiker's Guide is a mention to Goonhilly. So check out your volume, and it's there, right? All that time ago. And other things around it. And I've digressed a little bit, but the point I'm trying to make is that when Chris Bryant was welcoming everybody, he said, it doesn't matter what sector I'm talking about or meeting, if it doesn't have a research-led university at the heart of it, it's probably not worth doing. Now, I said thank you very much for those comments.
That's great.
What would you say?
Yeah, I'd say I'd shake his hand and thank him and slip him a tenner. But I would also say that it doesn't mean anything if you don't have good partners. A university can do a great deal, and there are miles of shelves of great ideas sitting on university library shelves and in their offices of things that never saw the light of day because they didn't think through how to become enacted in the real world. And that really does mean proper partnership work with businesses, charities, organizations of every sort. And this is it is too rarely put up front at the beginning of a research proposal. So we're getting much better at that at Exeter. And we lead the way in various fields on that. So we just need to keep doing that. And I mean, the space sector is a great example. The stuff that we do with machine learning around Earth observation data with those partners is really quite innovative and exciting. So more of that.
Thank you. That's almost certainly what I should have said, actually. But thank you ever so much. And listen, thank you, Paul, Dan, Torsa, Beccy, and Iain for those wonderful presentations and answering the questions. Thanks very much. A round of applause.
Thank you.
For them.